In this lesson, we're going to wrap up our look at nucleophilic substitutions, this time focusing on the substitution reactions of ethers. Just as we saw with alcohols, the direct nucleophilic substitution of an ether typically fails, and for much the same reason. The would-be leaving group of an ether is an alkoxide, and alkoxides are bad leaving groups, just as bad as the hydroxide leaving group found on an alcohol. Just like alcohols, ethers can be coerced into nucleophilic substitution under acidic conditions. If we look at the first example, we can see diethyl ether reacting with HBr to form an alkyl halide and an alcohol. The reaction is often referred to as cleavage because it essentially breaks the ether in half. The alcohol product formed in the reaction is not always isolated, and that's because, as we saw before, alcohols can also react with the halogen acids to form alkyl halides. So depending on the actual reaction and the specific conditions used, the alcohol could also be transformed into a second alkyl halide. Because ethers have two carbon-oxygen bonds, there's a potential for nucleophilic attack at two separate carbons. In this first example, the regioselectivity was not an issue due to the symmetry of the ether. The next example shows the cleavage of an asymmetric ether, having two distinct alkyl groups attached to the oxygen. Nucleophilic attack could occur at either site, the tertiary carbon on the left of the oxygen or the methyl carbon on the right. As you can see from the products, the reaction preferred to undergo nucleophilic attack on the more highly substituted carbon on the left, displacing methanol as a leaving group. As with all things, this regioselectivity can be explained if we look at the reaction mechanism. In the first step, the ether acts as a base and is protonated by the strong acid, forming an alkoxonium ion. The positive charge greatly enhances the electrophilic character of the molecule. At this stage, two possible reactions can occur. The methyl carbon below the oxygen could undergo a rapid SN2 reaction, displacing tert-butanol as a leaving group. The tertiary carbon to the left of the oxygen could undergo a rapid SN1 mechanism, displacing methanol as a leaving group. That means that this intermediate could potentially undergo a rapid SN1 or a rapid SN2 mechanism, and we've seen that problem before. Nucleophilic substitution on a secondary alkyl halide can undergo SN1 and SN2 at roughly similar rates. The difference here is that the two mechanisms would be occurring on two distinct carbons. Regardless, it still means this intermediate could undergo SN1 or SN2. And that means to figure out which mechanism is dominant, we need to look at the nucleophile and the solvent. In this case, the nucleophile is chloride, and while it's negatively charged, chloride is actually a fairly weak nucleophile. It's a very stable anion given the size of chlorine. Weak nucleophiles tend to favor SN1. The reaction solvent is implied to be water. Hydrochloric acid is aqueous. Water is a polar protic solvent, and polar protic solvents tend to favor SN1. So both the nucleophile and the solvent are pushing this reaction to undergo SN1 selectively. So in the next step, methanol is displaced as a leaving group to give a carbocation, which is then attacked by chloride in the third and final step, giving the final alkyl halide. If we look back at the first reaction, we can predict that the reaction would occur via SN2, and that's because the two carbons bonded to oxygen are both primary, and a primary carbon will undergo a fast SN2 and a slow SN1. We're going to wrap up our discussions on nucleophilic substitutions with a quick look at the reactions of epoxides. An epoxide is a three-atom cyclic ether. Epoxides are also known as oxiranes, and you can see the simplest one shown here. Epoxides are considerably more reactive than other ethers, and that's due to the tremendous amount of angle strain found in a three-membered ring. Epoxides are susceptible to ring opening reactions. Cleaving either of the carbon-oxygen bonds will break open the ring, relieving the angle strain and the torsional strain associated with a three-membered ring. There are several ways epoxides can be prepared. One way is via the intramolecular Williamson ether synthesis of a vicinal halohydrin. As you can see in this example, the alcohol is first deprotonated with a strong base such as sodium amide. The resulting alkoxide then serves as a nucleophile, attacking the adjacent carbon and displacing the halogen as a leaving group. You might recall that vicinal halohydrins can be prepared from alkenes in the halohydrin reaction. Another method for the preparation of epoxides is the direct epoxidation of an alkene with a peracid. As you can see from this example, the reaction is stereospecific. Here, a cis-alkene accepts an oxygen from the peracid to form a cis-epoxide, in which the two alkyl groups are on the same side of the ring. Likewise, reaction of a trans-alkene would produce a trans-disubstituted epoxide. The reaction mechanism is a rather strange one-step process. The alkene acts as a nucleophile, attacking the terminal oxygen of the peracid. The oxygen-oxygen bond breaks, and the electrons flow towards the carbonyl carbon to form a new pi bond. This forces the cleavage of the existing carbon-oxygen pi bond, making a new oxygen-hydrogen bond with the terminal hydrogen of the peracid. The electrons in the existing hydrogen-oxygen bond then flow back towards the alkene, making the second carbon-oxygen bond of the epoxide. The concerted nature of the reaction mechanism guarantees that both carbon-oxygen bonds in the epoxide are made at the same time, preventing free rotation along the carbon-carbon bond, thus preserving the stereochemistry in the reactant. A very commonly used peracid is metachloroperoxybenzoic acid, or MCPBA for short. So if you ever see MCPBA in a reaction, you'll know that it's just a specific peracid. Remember that epoxides are ethers, just particularly reactive ethers. And that means that epoxides will react with nucleophiles under acidic conditions just like any other ether. In this example, we see the ring opening reaction of a substituted epoxide with HBr. We can see that the reaction proceeds to give a vicinal halohydrin, placing the halogen on the more highly substituted carbon of the ring. This regioselectivity can of course be explained if we look at the reaction mechanism. And it's the exact same mechanism we saw for the acid-induced cleavage of other ethers. In the first step, the oxygen is protonated by the strong acid to form a cyclic alkoxonium ion. And if we stop right here, this might look somewhat familiar, because we've seen a positively charged three-membered ring before. The halonium ion intermediate formed in the halogenation of an alkene, and the mercurinium ion intermediate formed in the oxymercuration reduction. And if you recall, in both of those reactions, the next step was the nucleophilic attack on the more highly substituted carbon of the ring. Even though the oxygen has the formal charge, the electron deficiency is actually shared across both of the carbons of the ring. And because positive charge is more stabilized by a higher degree of substitution, more positive charge develops on the more highly substituted carbon of the ring. The nucleophile will thus be attracted to the carbon with more positive charge. So in the second step, the bromide attacks the more substituted carbon of the ring, making a new carbon-bromine bond, opening the ring via the cleavage of the carbon-oxygen bond to give the final product. So under acidic conditions, epoxides will favor nucleophilic attack on the more highly substituted carbon of the ring. Unlike other ethers, epoxides can actually undergo nucleophilic attack under non-acidic conditions. The relief of angle strain brought about by the cleavage of the epoxide compensates for the poor leaving group associated with an ether. The example here shows a substituted epoxide reacting with methoxide in methanol. As you can see, the reaction is regioselective, favoring nucleophilic attack on the less substituted carbon of the ring. This regioselectivity can be explained by looking at the reaction mechanism. Because there is no strong acid present, the epoxide is not protonated in the first step, and is instead attacked directly by the strong nucleophile. Because the epoxide is electronically neutral, there is considerably less positive charge development on the two carbons in the ring. In the absence of any major electronic influence, steric hindrance dictates the regioselectivity. It's simply easier, and therefore faster, for the nucleophile to attack the less sterically hindered carbon bearing fewer substituents. So in the first step, the nucleophile attacks the less substituted carbon of the ring, breaking the carbon-oxygen bond and forming an alkoxide. Because the alkoxide is a very strong base, it can be protonated by a weak acid such as a solvent molecule. Here, the alkoxide intermediate deprotonates methanol to give the final product. Alternatively, a strong acid can be introduced to the reaction after the initial nucleophilic attack. So under non-acidic conditions, epoxides will favor nucleophilic attack on the less substituted carbon of the ring.